Hello. Today we are going to introduce the rate law, and this is something that we'll go into much greater depth tomorrow and Thursday as well, actually. So today's stuff is important because it's going to be the foundations for that, but today's video will be significantly shorter for that reason as well. By the end of today's lesson, you should be able to say that I can determine the overall reaction order given the rate law for that reaction. And just like yesterday, we will start with a warm-up. So, thinking back to yesterday's lesson, what are the units for the rate of a reaction? I hope that you have answered that the rate is given in moles per liter times seconds. And as we'll learn today, the units are going to be, we'll talk more about it actually I think tomorrow, but the units are important to keep track of when we're talking about rates. So let's dig in. What is the rate law? The rate law is a function of reactant concentrations, product concentrations, and temperature. And typically the rate law, not typically, the rate law is unique to each reaction equation at a specific temperature. Specifically, the rate constant is temperature dependent. And typically rate laws are derived from experimental data. They're not something that you can find from stoichiometric coefficients. They're not something that you can find just by looking at a reaction. You need to have data. Today we're going to do the simplified version where we're getting some information that we will tomorrow learn how to find. So if you're given the reaction x plus y yields z plus w, our rate law is going to be, our rate is going to be equal to k, which is the constant, times the concentration of x to the m power, times y, the concentration of y to the n power. And m and n are the orders, which we'll talk about in just a second. Let's focus on k for a second. So as I said, this rate is temperature dependent, but another unique thing about it is even though it is a constant, it definitely has units. I know not all of our constants have units, but it has units, and its units are actually reflective of the overall order of the reaction. And so let's talk about orders. As I said, m and n, those exponents are the order with respect to x and the order with respect to y, respectively. To evaluate or to calculate the overall order of the reaction, we add those together, which, if you think about it from a mathematical perspective, this should be very familiar. When you're dealing with exponents and you're multiplying two values together that have exponents, we add the exponents together. Reaction orders are just a way to define how the reaction rate is affected by reactant concentration. And a little bit more specifically, we're going to talk primarily about first, second, and zero order reactions. So a little bit more about first, second, and zero order reactions. In a first order reaction, rate is directly proportional to the concentration of x. So the reactant x is going to directly affect how quickly or slowly a reaction takes place. In a second order reaction, the rate is directly proportional to the square of x. So that is, again, mathematically, if you think about it, that makes a lot of sense based on our the rate law formula, but it's going to affect more greatly the rate of the reaction. And one thing to note between first and second order that can often be confusing, as I said, you're often going to be working with a set of data when you're calculating rates and looking for orders. And so if you have a reaction or a reactant whose concentration doubles, and then you see a doubling in the rate that does not mean that that is a second order reaction, even though you've seen a doubling. That doubling in both the concentration of the reactant and in the rate indicates that it is directly proportional and therefore a first order. So it's important to remember that sometimes you'll see doubling, but that doubling is not indicative of a second order. It is indicative of first order because it is directly proportional. We can also have a zero order reaction rate, a zero order rate, and that simply means that the rate is not dependent on the concentration of that particular reactant. If you think about it again from a mathematical sense that we've got it written makes sense. Any number to the 0th power is going to be 1. So K times 1 is simply the rate constant times 1, which means that the concentration of X doesn't affect the rate. Let's look at one simple little practice problem, and then we will move on for the day. So if you're given the equation 5 bromine plus bromate plus 6 hydrogen yields 3 bromide plus 3 H2O, 3 water, and you're given the rate equaling K times the concentration of bromine times the concentration of bromate times the concentration of hydrogen to the 2nd power. What I want you to be able to do is to be able to look at that and get the rate orders of each of those reactants, and then therefore the overall rate order of the reaction. You should be able to get this pretty simply because we only have one exponent that's written out explicitly, and that means that we have several first orders. So if we look at bromine, if it does not have an exponent that's written out, that means it's got an exponent of 1. So our rate order for bromine is going to be first. You should then be able to look at bromate and say the exact same thing. It's also a first order. And hydrogen is the only of our reactants that has an exponent, so we know that it is a second order. And to find the overall rate order, we simply add those 4 numbers together to get an overall rate order of 4. Like I mentioned earlier, this information is not necessarily how you'll always get this, not how you'll always work with finding the rate orders of each of the different reactants. Usually you are going to be gleaning that information from a set of data, which is exactly what we're going to work with tomorrow. So this is important to understand so that we can build on it tomorrow.